Let's try a couple of problems. What is the probability that you will pick a king of spades from a normal deck of cards, jokers removed, in a single draw? Well, as we know, there are 52 cards in a normal deck of cards with the jokers removed, and the probability that we would then pick the king of spades, since there is one king of spades in the deck, would simply be 1 out of 52. What is the probability you will pick an ace from a normal deck of cards, jokers removed, in a single draw? Well, as you recall, in a normal deck of cards, there are 4 aces. So the answer to this question is there are 4 ways out of 52 that we can pick an ace. What's the probability you will pick a red chip from a bag containing 8 red chips, 5 white chips, and 15 green chips? Well, if you note, 8 and 5 is 13, plus 15 more chips is 28 chips exist in the bag. So if we reach into the bag to draw a chip, there are 8 ways out of a total of 28 to pick a red chip. You will pick an ace followed by a king from a normal deck of cards, jokers removed, in 2 draws without replacing the first card. Well, you can see that this probability question is much more complicated than any of the first 3 that I've shown you above. So we're going to have to examine some more facts about probability before we can answer or tackle this question. The probability question we just looked at is what we call a combination experiment. So let's take a look at that type of situation more carefully. First, let's recall the following. What is the probability of rolling a 5 when rolling a single die? Okay, as we know, there are 6 faces on a die. 5 is one possible outcome. Therefore, it is 1 out of 6. What is the probability of rolling an even die when rolling a single die? Since there are 3 favorable outcomes, 2, 4, and 6, which are even, out of a total possible number of outcomes of 6, of course the answer is then 3 out of 6, or 1/2. What is the probability of rolling a 7 when rolling a single die? Well, of course, there is no outcome 7 on a die. Therefore, the probability of rolling a 7 is 0 out of 6, or simply 0. It's impossible. What is the probability of rolling an odd die when rolling a single die? Well, since there are 3 potential outcomes that are odd, 1, 3, and 5, the probability of rolling an odd die will simply be, once again, 3 out of 6, or 1/2. What is the probability of rolling an even die, or 4 or 7, when rolling a single die? Well, examining the outcomes, we can't have a 7. 4 already is an even outcome. So again, there are 3 potential even outcomes, 2, 4, and 6. So once again, the probability here will be 3 out of 6, or 1/2. What is the probability of rolling an odd or even die when rolling a single die? Well, the outcomes on a die are either even or odd. So therefore, there are 6 ways out of 6, or a probability of it absolutely happening of 1. The basic counting principle of outcomes. How many outcomes result from spinning the spinner shown twice? You probably recall from high school that for each of the 4 outcomes shown here, blue, green, yellow, and red, there will be a blue, green, yellow, and red outcome in the second event. Well, if you recall from high school, you often drew a tree diagram to represent all the possible outcomes for this 2-stage experiment. So let's take a look at that. We would draw 4 branches representing the first event. Red, yellow, blue, green. And off of each of those, since if you first spun a red outcome, in the second event you have 4 potential outcomes that you could spin. Red, yellow, blue, green. Same here. Red, yellow, blue, green. Red, yellow, blue, green. Same here. Red, yellow, blue, green, and same down here. 4 branches here. Red, yellow, blue, green. If we count all the branches that we see on this diagram, we find that there are 16 total outcomes that exist for spinning the spinner twice. Let's look at another situation. How many outcomes result from rolling a single die twice? Well, probably one of the simplest ways to look at this situation is to list an entire sample space of all the potential outcomes. So let's take a look at this diagram. As you can see here, the sample space contains 36 outcomes, 6 by 6, or 36. And let's look at one other example. How many outcomes result from picking a card from a deck of cards, replacing the card, and then picking a second card? Well, I'm sure you recall from our earlier discussions that there are 52 cards in a regular deck of cards with the jokers removed. So in the first stage, you have 52 different possible outcomes. If you put that first card back, then in the second draw, you also have 52 cards that you can pick from. Is the answer 52 plus 52 or 104 outcomes for the 2 stages combined? Well, I think you can tell from what we've done so far, you have to multiply 52 times 52. So the correct answer for the number of outcomes in this 2-stage potential experiment is 2704, or 52 times 52. So our discussion about outcomes leads us to the basic counting principle of outcomes. If a first event A has n outcomes and is followed by a second event B with W outcomes, then the 2 events combined will have n times W, or NW outcomes. This rule holds true even if there are more than 2 events. Let's take a look at this. Here is an experiment with 3 different events. Spinning the spinner, rolling the die, and picking a card. And from what we've just discussed, you can see that the number of outcomes in this combination experiment will be 4 in the first event, 6 in the second event, followed by 52 in the third event, or 1,248 possible outcomes. If a particular probability experiment involves spinning the spinner shown twice, we know that there are 16 outcomes for the 2 events combined. 4 in the first event, 4 in the second event. 4 times 4 gives us the 16. Let's list the sample space for this experiment. And there they are, all 16 outcomes. Using this sample space, let's find the following probabilities. What is the probability of us spinning yellow followed by white? Well, let's see. There aren't any white outcomes, right? So the answer to that would simply be 0. It can't happen. What is the probability of spinning red and then spinning green? Well, looking at our sample space, the outcome red-green is there once, so it's 1 out of 16. What is the probability of spinning green-green? Well, as you can see, there is one outcome of green-green, so that also is 1 out of 16. How about the probability of spinning the same color? Well, let's see. There's blue-blue, green-green, red-red, and yellow-yellow. Therefore, there are 4 potential outcomes out of 16. What is the probability of spinning any color followed by red? Well, it doesn't make any difference what we spin the first time, so as long as we get red on the second spin, we're all set. So how many different ways do we have red on the second spin? 1, 2, 3, 4 ways. 4 out of 16. And how about getting different colors? Well, wait a minute. If the same color, there are 4 ways out of 16 to get the same color, it would seem that there must be 12 ways out of 16 not to get the same color. So if we look at that, different colors, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 ways, as we can see from counting them. Now let's think for a minute. Let's examine each probability that we just did, one event at a time. What is the probability in this first example here of getting yellow? Well, it's 1 out of 4. What is the probability of getting white? It is 0 out of 4. All right, we'll just leave those there for a minute. Let's do this for each situation. What is the probability of spinning red in the first draw, or first spin, excuse me? 1 out of 4. How about green in the second spin? If we consider it as a separate event, 1 out of 4. How about green followed by green? Well, for the first event, it would be 1 out of 4. For the second event, it would be 1 out of 4. How about getting the same color? Well, we have 4 colors to choose from, so there's 4 ways out of 4 in the first event of getting a color. And then to get the same color over again, there's only one way we can match the color we got in the first spin, so that would be 1 out of 4. Down here, any color, well, let's see. We can pick any color first, so that'll be 4 ways out of 4, okay? And red, there's only one way we can get a red one, so that's 1 out of 4. And looking at different colors in the first event, okay, we would roll or spin, excuse me, a color. And in the second spin, there would be 3 ways out of 4 not to match the first color that we did spin. Okay, so that would be 3 out of 4 for the second event. Now, looking at these individual fractions for the individual events, I think you can see there's something I can do to those individual fractions to get the answer I obtained or observed when I was doing the combination experiment by observing the sample space. What do I have to do to 1/4 and 0 out of 4 to get 0? Well, I think you can see that all I have to do is multiply these 2 individual probabilities together and I obtain the correct answer. Does it work here? It does. Does it work here? Again, you can see that it does. 1/4 times 1/4 is 1/16. 4/4 times 1/4 here will give us 4/16, and so forth. So it is easy to see then that if I want to know what the probability is for the combination experiment, I can take each event separately, get their individual probabilities, and multiply them together to get the answer.